Today I want to discuss identifiability in mixture models. You may recall that a statistical model is identifiable if two different values for the parameters, any two different values for the parameters, always give rise to different probability distributions for the data. Now, unfortunately, mixture models are not fully identifiable. So let me show you three ways in which mixture models are not fully identifiable. One of them is what's sometimes called label switching. And to illustrate label switching, let's look at a mixture of two normals. For example, call this f1 of x. And let's say that it's a mixture where the first component has 70% probability. It's a normal with variance 1 and mean 0. So this is the density. And the second component has mass or weight 0.3, maybe a standard deviation of 2, and a mean of 1. Okay? So in the notation that we have been using so far, this would be a mixture where omega 1 is equal to 0.7, omega 2 is equal to 0.3, mu 1 is equal to 0, mu 2 is equal to 1, sigma 1 is equal to 1, and sigma 2 is equal to 2. So keep these numbers in mind for a second. Now, I could write a second mixture, f2 of x, that is essentially the same expression that I have up here, but I'm just going to flip what I'm calling component 1 and what I'm calling component 2. So I'm going to say this is 0.3, 1 over square root 2 pi to exp 1/2 x minus 1 divided by 2 square plus 0.71 over square root 2 pi exp minus 1/2 x squared. Now, if I'm again going to try to use the notation that I had before to kind of recognize what the terms are, if I write it this way by just switching the order of the terms, what I have is my omega 1 is 0.3, my omega 2 is 0.7, my mu 1 is 1, my mu 2 is 0, my sigma 1 is 2, and my sigma 2 is 1. In other words, what I was calling 1 here has become 2 in here, and what I was calling 2 here has become 1. Now, the mixture, these two are exactly the same models. There is really no practical difference between them, except for the labels that I'm using for the components. And essentially, if you have more components in the mixture, you're going to have many more permutations that you could do of the terms that, at the end of the day, represent the same mixture. So the fact that you can switch this order, that translates into basically switching what names you use to label the components, is what we call label switching. So label switching is going to have a number of implications for us later on. One of them is that, for example, some of our algorithms that we're going to use to fit our models may give us two answers that represent, for example, the same mixture, but where the only thing that is really different is the order in which the component appears in the response. And we need to be able to recognize those two answers that just differ on the order as essentially representing the same final model that we're working with. So this is something that we are going to have to keep in mind when we do computation with our models all the time. Label switching is not the only way in which identifiability problems come up when working with mixture models. There are at least two more ways in which these identifiability issues can manifest. And again, let me illustrate them with a little example. So let's start with our same mixture that we use to illustrate label switching. So the first component is going to be a mixture of two normals, with the first component having or being a standard normal. And the second component being a Gaussian with mean 1 and standard deviation 2. Okay. And let's consider another two mixtures. So one of them is going to be of the form, it's going to have three components. I'm going to call this F2. The first component is going to be exactly the same. But what I'm going to do is I'm actually going to split this component into two pieces, say one that has weight 0.1 and the same mean and standard deviation. And then a third component with the same parameters but the leftover weight. So clearly, this is a mixture of one component. This is a mixture of three components. In practice, we can understand that because the parameters are the same, I can collapse these two terms into one. But from a representational point of view, these are different models. So this is another way in which the model is not identifiable. We have different sets of parameters down here, actually even different values of k, but they both correspond to the same density at the end of the day. In practice, this becomes a problem when you're feeding a model in which you have, for example, overestimated the number of components that are included. And one of the things that may arise is that some of the components have, if not identical parameters, at least parameters that are very, very, very close to each other. And that in practice could be collapsed into a single one without really affecting the fitting of your model. So this is going to become important, particularly when we think about how to select the number of components in the model. Another way in which this can arise is that, of course, I can retain my original components. So call this F3 of x, just another mixture. So I can work with the mixture that I had before. To x. And I can add 1 or 100, if I want, components that have 0 weight. So I can add 0 times, for example, 1 over square root 2 pi times 3 x minus 1/2 x minus 100 divided by 3 squared. So again, from a representational point of view, this corresponds to a three-component mixture. But because this weight is 0, it's clearly in practice just identical to the first one that we started with. Again, this may arise in practice. For example, you may not have weights that are exactly 0, but if you overestimate the number of components that you have in the mixture, you may end up, one possibility is that you end up in a situation like this, but another possibility is that you end up in a situation that looks a little bit like this, where you have one or various components that have weights that are really, really, really tiny, and for all practical purposes, 0. And even though you think that you're fitting a model that has, say, 3 components, in practice you end up fitting a model that has only 2 components. So these 3 ways in which mixture models can be non-identifiable: label switching, components that have the same parameters and just split weights, and components with 0 weights, are things that you need to keep in mind when looking and interpreting results for inference in mixture models.